this thing about absolutely continuous function. So let's start again with the definition, no? So let's say f from some interval, let's say a b into R is absolutely continuous, just to shortness, if, so remember that the thing is that we need this to be the integral of an L1 function. And so we know that for L1 function, whenever the interval integration is small, well, okay, you can make the integral to be arbitrarily small if the set of integration has small measure, being L1. So here how to restate everything without avoiding the integral is that if for all family of intervals I intervals such that, so it should be like this. If for all epsilon, for all family there exists delta, for all family of intervals is that the sum of the length of this interval is less than delta, the sum of the variation f, so let's say each I is ai bi, f of bi minus f of ai is less than epsilon. So it's very close to, well, like the absolute summability, no? That you don't care how you add the intervals in order to be small. Because the continuity, you just, well, clearly if you partition the interval of continuity into smaller intervals, and then you add according to the R ordering, certainly you obtain less than epsilon. But here, essentially it tells you that no matter how you sum up this variation, they are small. Okay, so that's the word absolutely continuous. And also, well, there are some other reasons that is tied to the mesh theory. So now the main theorem we want to prove is essentially that, well, what we know here, recall, well, the following picture, no? So we have the BD functions, and are the one with the total variation of f in the interval is less than plus infinity. And certainly, well, you have, they are difference of two monotone functions, so let's say these are the monotone functions, increasing or decreasing. And then you have a transversal set, which is this absolutely continuous function. So we proved that certain is BV, and then it is the difference of two monotone functions. But you have monotone functions which are just BV and not absolutely continuous. Vice versa, something decreasing is not monotone increasing. Okay, so today we want to prove the fundamental theorem of calculus, and now you see why this condition is very important. So let's start with the theorem. Yeah. If they state something, okay, let's say f is absolutely continuous. This is equivalent to for all h the function diff f is x, which is f x plus h minus fx divided by h, is uniformly integral. So, what does uniformly integral mean?
If the measure of a set is less integrals.
No matter what is h. No. So this is a family which depends on h. For each h, you have a function which is called the incremental ratio of f. And to be in uniform interval means that if the set, well, would be the same set as you expect. If the set has measure less than delta, the integral of this function will be less than h, so the epsilon, no matter what is h. Okay? So let's jump a little bit forward. Why do you think this will be the key point in proving what we need to prove? We need to prove, of course, so we need to prove a remark. This is the key point in proving f of y minus, sorry, f of x minus f of, say f of y, doesn't matter, minus f of x equal integral to f prime z is x to y. Y would be the fundamental point.
Because when we take the limit of h tends to 0, it will not become problem because h.
Exactly. What was the problem when we take the limit of the incremental ratio inside the integral? We use Φ2, if you remember, no? And so Φ2 gives only half of the inequality. We can use Φ2 because we can take just a to be the difference, so a function to be the difference of two monotone functions. At the end, we need to prove for monotone functions which are absolutely continuous. And the problem is that we cannot pass to the limit a priori unless we know something which avoids the mass to go to infinity. Well, now we are in a compact set, so no matter. You cannot escape horizontally, but you can escape vertically, and this will be the tool which allows you to avoid this escape vertically. Okay, so proof. Okay, let's start with well, the trick is always the same. So let me say the trick first. So the trick is the following. So I have this relation. So the integral from, let's say, AI to BI of the difference HF is equal to, okay, let's do graphically. I have AI, let's say H positive, doesn't matter. And then what I have, I compute for each x plus h, so the difference here minus this guy divided by h. Okay, so essentially what I'm doing, I'm integrating along this, along this, which is a plus h, b plus a, bi plus h, minus this integral here, no? Divided by h. So because you think, so I'm integrating for each x, this minus this one, which is essentially as integrating. So I'm adding all these points and subtracting all these points. Okay, otherwise you just write, so 1 over h is f x plus h minus f of x dx. This is by definition. This is equal 1 over h. Now the common intervals, okay, this is a plus h, b plus bi plus h, f x minus the integral from ai, bi, fx dx. And this is equal to what is left? Integral b I plus h, the integral ai plus h. Okay, I say that this is the fundamental trick. Why? Okay, let's start. Which one you prefer, to be absolutely continuous or the other one? Let's start if this is, it's easy now to see from this is uniformly integrable in some sense, no? Than the other. Well, if the HF is uniformly integrable, what I obtain? Okay, let's apply the definition. So for all epsilon, there exists delta. Okay, if the sum of intervals, so let's say the sum of bi minus ai less than delta, then this integral here of the difference, okay, I can put the thing outside, is less than epsilon. Okay, now I use this equivalence, and this implies the sum over I, 1 over h bi plus hf minus 1 over h ai plus hf is less than epsilon. Okay. And then, okay, it's done. Why? I just do a limit. You see which limit? F is continuous, no? Because
It's absolutely continuous.
yes, but no, I don't know yet if it's absolutely continuous. I know that F is continuous, and the difference is uniformly integrable. I want to say, okay, then it's well, I don't even need the I take continuous because I want to have an, but I don't need it. Let's h go to 0. No? If h go to 0, this converges to f of bi minus f of I, and is exactly the definition here. You see? Okay, so limit for h tends to 0, and f continuous implies, okay, as an exercise you can avoid the continuity. I just don't want to, because I know that this converges almost everywhere, and then I deduce that f as a representative which is absolutely continuous up to a set of, f is absolutely continuous up to a set of measure 0, so it is continuous. So, because every time I do integrals, I remember that everything is decided up to set of measure 0. But let's avoid this. This is it's just a, how to say, it's just the language of measure theory. So this implies sum over I, f of bi minus f of ai. Sorry, I write here less than epsilon. Okay, so it is absolutely continuous. Okay, let's do the rest. The rest is that I go back, no? Of course. Okay, let's go. Let's answer this functional relations, and then the 2. So now what I know. Okay, I would like to write this for averages, no? So give me h. I have this, and I want to say that this implies this estimate for average. Then if I have the estimate for average, well, I just do the same trick. This is an estimate on the difference. Okay, so why this implies this? Okay, f is absolutely continuous. And so now let me write sum over I, 1 over h bi plus h fx dx, 1 over h ai plus h dx. Okay, well, I can do the following. This is the integral. I'm integrating here, here, minus here. Well, I just say, okay, if you pick a point here, you pick the same point translated by vi minus ai. No? So I can relate the 2 points like this one. So this is equal to the sum 1 over h, and then I'm integrating from 0 to h, and then it's f of bi plus x minus f of ai plus x. Okay? Just with the modulus. Well, and this is less or equal than 1 over h, integrate from 0 to h, the sum f of vi plus x minus f of ai plus x. And then you see, these are the same intervals I'm considering here. Translate. So is the measure changing? Is intersection invariant? Yeah. So this is less or equal than delta. At the end, delta 1 over h integral is less or equal than epsilon. Okay, so I have that. This implies this one, which is equivalent to the difference, and with the modulus outside, but we know that that does not change because we can take positive or negative. Okay, so this is the key point. Now we can prove finally the theorem. Oh, we deduce something. Well, okay, no, we deduce. Let me make the observation. So, which is being used there several times. The integral from a to b of the difference of f is equal to, well, so it's what is written here. 1 over h, the integral from b plus h of f, 1 over h, the integral from a plus h of f. It's what is written there. So we have, and this is something like the approximate fundamental theorem of calculus. So let's give a name. This is the approximate fundamental theorem. No, because it's not given for a point-wise value, but for average, I'm fine. So the theorem is that I pass to the limit. F is AC. Then, well, we know that it holds for every x, so f of b for all dA, f minus f of a, the integral from a to b, f prime x dx. Okay, we know that this implication was already seen, no? Because it's the implication that this is an L1 function, and then I certainly have uniform integrability. So we have to prove the other one. Let me see. Okay, we already asked this when I asked why it is the key point.
I don't understand the question.
The question is that I'm saying that, well, when I before doing the proof, I said, why this is the key point?
Yeah.
Why is this the key point? And you answered correctly. Remember, we said, well, uniform integrability can pass to the limit. So what I have to do now?
Prove that
So I leave you as an exercise. It's already because we know the differential of H is uniformly integral. We know that almost everywhere converges to the gradient, to the to the derivative. No, because if it is absolutely continuous, it's the difference of two monotone functions, differential almost everywhere. So this converges to the integral of f prime. And well, this converges, the average converges to the value. So it's an exercise. So does everybody agree that it's an exercise, or no? I want to see it. You want to see the proof? Okay, so you do the proof. So let's put the ingredients. So actually, tell me which ingredients we have. Okay, this is the first ingredient. Approximate formulation. Let's see. Which is this one. Okay. Second one. Do you agree that the problem is to let H go to 0? So the approximate formulation is the following. The integral from A to B, f x plus h minus fx divided by h is equal to 1 over h from b to b plus h fx dx minus 1 over h a plus h fx dx. Do you agree that I would like to go to 0 with h? Does everybody agree? It's h going to 0, no? Because this should converge to the derivative. And this should converge to the value. Okay, which is the easy part? This converging to the values, or this converging to the derivative? The second is easy. Why? F is continuous. If f is continuous, the average converges to the value. You agree? So when h goes to 0, this converges to f of v, and this converges to f of a. So the problem is this one. It's okay? So I have this one. What is the limit? Do you agree that almost everywhere sounds so, but why?
Because f is AC, so B, so.
So, yeah. We have seen that, well, f is AC, so it is BV. BV is the difference of two monotones. For monotones, the derivative exists almost everywhere. You remember, we proved that the set where the upper derivative, lower derivative are different as measure 0, because you have the contradiction. So on one hand should be larger than beta, on the other should be smaller than alpha, and that's a contradiction. Also 1 over beta, 1 over alpha. So, how to pass to the limit? We have the third basic ingredient is the uniform integrability. We'll see right now. So diff So which theorem should I apply now? The Vitali theorem, which is the generalization of the Lebesgue theorem. Lebesgue theorem you have a boundance for a function, and certainly is uniformly integral because it's bounded by an L1 function. So apply Vitali, which tells you that the limit of this guy, so that question mark is exactly the integral of f prime x dx. So all the ingredients are on the back. Are you okay now? Okay, so there is still one question. Is the function we satisfy, so suppose I have another function, so I know that this equation is satisfied by f prime. That could be a function which is different from f prime. What do you think?
If another function satisfies that, then
Yeah?
as you said, it should be equal to f prime almost everywhere.
Why?
You can take derivative.
Hmm?
You can do derivative. Change b to some variable.
You take derivative, yes, you have to prove that the integral from a to x of any function g has derivative equal to g. Well, yeah. Which can be done, but I don't know if I gave you the tool. I think not next this week, but before the end of the course, yes, you have the tool, and then the answer will be straightforward, yes, of course. But now I don't know yet because so the question is the following: the derivative with respect to x of the integral from a to x of g is equal to g x almost everywhere. So this is the question, no? You said I take derivative, which is exactly what I do. So I give me g, I find the primitive function, and I take the derivative, I should get g again. And the answer, yes, is yes once we know what is a Lebesgue point, but yet we don't know what is the Lebesgue point. So we have to use another tool, and the tool is that, in my opinion, is that we can take intervals, no? So this implies, so if f of y minus f of x is equal to the integral from x to y g z dz. On the other hand, this is certainly integral to x to y f prime z dz. I obtain that for all intervals the integral from x to y g z minus f prime z dz is equal to 0. Without resorting to a little bit more advanced tools. Certainly, this is true, no? Because the definition, if this is equal. Okay, and now?
It's also true for all measurable set.
That's true. Why?
Because a measurable set is a G-delta set and a measure zero set.
Yeah. So from this it holds for all open, no? Okay. If this is 0, then open is a union of intervals, countable many, and and it is for all open, I can take the regularity of the integral. No? So if a set is shrinking, the integral is shrinking, or the continuity, whatever, because here I can apply even Lebesgue theorem. This is L1. Then for all E measurable, and then
we take E to be F minus F, G minus F prime positive.
the positive part. Yeah. Then E, let's say E plus is equal to F, the set where F minus G is larger than 0, and E minus is equal to the set where F minus G is less than 0, and then we discover that the measure of E plus is equal to the measure of E minus is equal to 0. Because if they are non-zero, I'm integrating something positive, and then I get something which is non-zero. Yeah, this is the... Okay, so corollary. So, what is written down there? The derivative. So, yeah, so the answer to the question is yes. Then it is complete now that we are not the theory. So we know the class, the derivative is unique, vice versa. If it is the integral of something, then the derivative is exactly the integrand. And let me tell you the future plans, just to let you digest, because we are doing a lot this year, so I'm a little bit scared. I hope you follow. So now we need still one class of functions, which are convex functions. And convex functions are fundamental because, well, there are, I don't know, uncountable functional estimates based on convex functions. And then I would like to do the Bell category theorem. Who knows Bell category theorem? You know? No, you know. You need to go to know, because it's a fundamental tool for proof existence of things. And then we do some, let's say, some a little bit more refined tools for measure theory, which are Lebesgue point, continuity or Lebesgue points, and the Jordan decomposition theorem for general measure, Radon-Nikodym, which is Radon-Nikodym is an extension of this theorem in some sense, where instead of integrating in G, I integrate with respect to measures. And finally, the Fubini theorem, so the fact that you can iterate, the integral in the plane is the iterative iteration of two integrals. No? You integrate in one line, then you integrate in the other. And that's all. So I think, and then I really would like to have the last lesson to see some example of the exam. Then I send you, if somebody gives me an email, I can send you some exam text just to train. Okay, and so how is the thing up to now? More or less? More or less? More or less than more? Okay, let's do the convex function. Convex function is light, so we relax. Definition. phi, okay. So let's say from A, B into R is convex if for all lambda in 0, 1, x, y in AB, phi of 1 minus lambda x plus lambda y is less or equal than 1 minus lambda phi x plus lambda phi y, which is an almost incomprehensible definition until you do a drawing. So let's say this is A, B. You take 2 points, x, y, and now you take, so this point is a linear combination, so since it is lambda less than 1, is a point in between. So this point is 1 minus lambda x plus lambda y. Do you agree? No. This is the linear combination. It's called convex combination, by the way, of x, y. And then, so the value here is below, and this one is the value on the segment connecting phi x to phi y. So this value here is 1 minus lambda phi x plus lambda phi y. No? So this is the meaning of the definition. If you give me 2 points, I take the segment connecting the 2 values, and the function is below for all this interval, this set. So the values here are below that function. Equality is equivalent to, you take the epigraph of f, epi phi, which is all the y is the couple x, y, such that y larger or equal than phi x. Is convex in the standard sense. And convex means give me 2 points, the segment connecting them is inside the epigraph. And you see, since everything is below, certainly is the same definition. Okay. So now let's call this point Z. So, and then the first passage is that I want to find lambda given Z in between. Well, okay, this is something because lambda then is equal to, okay, is x minus, sorry, is lambda, is y minus x divided Z minus x. Now we substitute, so I get 5z less or equal than 1 minus lambda with this thing is y minus z, y minus x, 5x plus lambda, z minus x, y minus x, 5y. I'm just changing instead of using lambda as independent, I use z. And then I get lambda. Okay, and then here I can rewrite, I throw everything on the other side. So it's phi z minus phi x divided by z minus x. Phi y minus phi z divided by y minus z. Well, and this is another definition. So what is the meaning? This one is the slope of this segment, and this one is the slope of the other segment.
The derivative is increasing.
Yes. Yeah, the derivative is increasing. Let me see if I do something before. Okay. So proposition, I deduce is phi is continuous. So is C1. And phi prime is increasing. Then, okay, phi is convex. And this is in some sense the implication because of regularity. And then this I leave as an exercise, because this is classical. So vice versa, I know that, well, I don't know yet that the derivative exists, no? I need to work a little bit. So I'm asking you, what would be, in your opinion, the you see what is the point. I can write the theorem, but I prefer you to think. The point is that I don't know if the derivative exists.
No, it's monotone.
Oh, yes, it's monotone.
You can prove it's monotone.
It's monotone in which sense?
What?
Still is not the derivative. You what you want to say is it's right, but
If it's continuous, it's monotone. Completely monotone.
if the derivative is continuous.
No. If the function is continuous, then a convex function is monotone. A convex continuous function.
The convex continuous function is monotone.
What?
No, the parabola. Parabola?
Yeah.
No. Okay, we need to. Okay, let's start with something. Let's construct the property. At the end, we have to write a sentence which is correct. And the problem for me is that, I tell you, I don't know, I know just that thing, and I would like to state something similar to this proposition, but clearly I don't want to have C1, because C1, well, so let's start with, for example,
Maybe.
let's say with first lemma. Or you can tell me what you would like to prove first. You have a you guess a property, and then we can try to prove it.
Well, no. I think that a convex function cannot change the monotony more than one. I don't.
Yeah.
If you do that, then it will necessarily cross somewhere.
Yeah. And how to prove that?
Yeah.
Yeah. If some point is positive, from then onward is positive, and vice versa. That's true.
So we can break the interval and the
Okay.
interval.
Yeah, it's a nice
both
property.
is monotone.
So let's say lemma 1. Lemma 1. Phi, so let's take like this. There exists x bar in AB such that phi is decreasing for x less than x bar, and phi is increasing for x greater than x bar. How to prove that? Well, we deduce that later, because there is some better property. So I want to finish the comment. Okay, but okay, this is correct. So let's forget about the proof. Let's go on with the guess of the properties, and then we choose which one it's easier to prove, which implies the other.
If we assume this, then it's okay.
This is okay.
Yeah, but then the proof follows because it's monotone and two intervals. So the derivative exists almost everywhere in each interval. So it exists almost everywhere.
The derivative exists in almost everywhere. You said this property. The derivative exists almost everywhere if it is monotone.
Yeah.
Okay, the monotonicity, how to get this? So you take what from this one?
No, we are saying that you told me we assume it, that it's increasing in the first and decreasing in the other. No, it means that it's monotone.
Okay, 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 and then the derivative exists almost everywhere on one side, on the other. Okay, yes. Consequence of the fact that it's monotone. So, for example, don't you think that phi is continuous?
What?
Phi is continuous.
Yes. Mm-hmm.
Is phi continuous? Why?
This continuity point is very right.
You see, I prefer a little bit than the continuity because I'm fine with, with the definition. Okay, how to prove that? This, let's see this. So take a point. So this is graphically, we do it graphically. We take a point x, and now let's look. So from what I take a point, so let's say this is the point z. If I take a point before, I get this segment, okay, this slope, and I'm sure that all the points here, they are above this slope. Do you believe? Because if there is a point below, I don't have this inequality. So the points live here. On the other hand, take a point here, take the slope, and I'm saying that all the points should live inside here. Are you okay for this? And on the other side, so I have 2 points, x, y. I have the 2 slopes. So this is phi z, phi y, phi x, and I'm saying that the function should live inside this butterfly shape region. Do you agree? Okay. Does that imply that it is continuous? Yes. Does that imply something more?
Yes, the left derivative and the right derivative should exist.
Should exist, yeah, that's true, but even it is bounded. The derivative is bounded. So for any, if I fix a compact set, I have this thing is uniform. And if the derivative is bounded, it means it's continuing. The derivative is bounded, then it is Lipschitz. Yes. So it's Lipschitz in every compact. We need to, because it can go to infinity like this, no?
Yeah.
Compact subset of A. Oh, and this is an important point.
It's absolutely continuous.
Yeah. Then it's absolutely continuous. And now I have the derivative. And now I'm fine with this lemma. Because now I discovered that the derivative is, if I have the derivative, I can take limits here, and I get derivative is increasing. And if the derivative is increasing, this implies, no, because at some point is 0, so I can cancel this lemma and say that the derivative phi is Lipschitz, so phi, the derivative of phi is monotone. And now we have, now we are really in business. Is continuous and phi prime is monotone. So we can even improve. So corollary. Well, now we have all the properties of the monotonicity. So the left and right derivatives, they exist. And the derivative, so they are different only encountering many points. Because now I apply the property of monotone function to the derivative. The monotone function has right left limits. And well, if I use the same for this, I get that phi prime from the left or from the right exists everywhere. So phi, the left, right, derivative exists everywhere, and they are different in at most countable set. So now the picture is much better. So let's do a picture of function. So a function can go to plus infinity, but cannot go to minus infinity, because otherwise you have a big trouble here. Well, and the limit here, well, it can converge, doesn't matter. And well, you can have some points where the derivative has a jump, or the derivative can even be the Vitali function, just a monotone function. Okay.
Phi is belong to C2. Then phi belong to C2.
No, because
Because derivative is monotone.
but is this also the converse, and vice versa.
Now, you mean that since C prime is also monotone,
So
then phi, then the second derivative also exists almost
you're
everywhere.
answering one.
Yes, yes. The second derivative, but it's not C2 then.
It's almost everywhere.
The second derivative exists almost everywhere, but doesn't mean that the function is C2. Take the Vitali function. The Vitali function has first derivative 0, and it's not C1. So as an example, indeed, let's build this is usually a nice example. So what is the convex function and here I have a trouble because in the text I think since they are in different chapters they use the same symbol. Convex function phi such that phi prime is equal to the other phi, the Vitali function. The Cantor, Vitali, and whatever that is, function. So how to build such a function? Well, we know it exists.
Should
definition.
Yeah.
Prime was the
Yeah, we have to apply the definition. Yeah. So at the beginning, we have that the function is a parabola. Doesn't matter what is the constant, because the initial iteration is x, and the integral of x is x squared half. So the second iteration is that we let the thing to be 0 in 1/3, so it becomes flat. And then what I do here, I increase this cannot be. I increase the slope of these parabolas. Then I repeat the same. Now, let me make something larger, otherwise you don't see the construction. So I flatten here, and then I have to increase the parabola. Because remember that in the iteration, these parts are linear. I just increase the slope. So I increase the curvature. And then here it becomes linear again, and then I increase. It's difficult. So at the end, I have a function which is is made of segments. So in each of these segments, the second derivative is 0. Okay. The measure of this segment is 1. So the second derivative of the function is 0, but the function is not a linear function. So in some sense, the second derivative of this function is concentrated in this very strange Cantor set. So it lives in this measure 0 set. It's a strange function. Okay, so to end this chapter, we see the most useful estimate for convex function, which is Jensen inequality. I think it's the Jensen inequality. And this is the most useful. If phi is convex, define it on R, and F is bounded, then bounded integrable, the integral of phi of the integral is less or equal than the integral of phi over f. And if you will, I think more than 50% of the functional inequalities you see, they depend in some way on the other of this, by choosing phi in the smart way. Of course, you have several convex functions, for example. Well, the exponential function. The exponential function gives you the estimate in the inequalities in LP. Well, all the inequality. Okay, proof. So the trick is that take that. Okay, I choose the point. yeah, I want you to reach the point. So let's say that m is equal to this quantity, which is less than plus infinity. And now I have a convex function. So I take a segment which is, well, a curve which is below the function in that point. Can you give me a curve? Can you give me a slope? So I'm saying that it holds for some p, phi of y, let's say phi of x, but let's say phi of y is greater or equal than phi of m plus p y minus m.
Why not? It's not sufficient to prove it only for simple functions.
Yeah,
The inequality?
Yeah.
Yeah.
It's not more.
This is really straightforward.
Ah, okay.
For simple function, yes. Well, let's see for simple function. Okay. So assume that this hold. Now, write for f. So phi f of x is larger than or equal than phi of m plus p f of x minus m. Integrate. The integral of phi f of x dx from 0 to 1 is larger or equal than, okay, the integral of m, this is constant, so it's phi m. And this is p. Now I have the integral of f minus m. But m is equal to this guy, so this is 0. And that's the inequality. So we are left just proving that this hold. So for any point, there exists what is called a supporting line to this point, which is m phi of m. And I'm saying that is inside here, or is inside that the lemma that I cancelled, that if there exists the right and left derivative.
Phi prime of m.
But if does not exist,
Let's say the life of
the left or the right. So P can be taken the left derivative, so let's say left derivative and the right derivative. This is something in the exercise.
We can change the inequality.
Why?
We can, can we find another p?
There are several. Okay, let's see this point, and then we go back to this inequality. There's something not in the program, but so let's use it. So from this inequality, I know that the derivative is increasing. So take a point, let's say x bar, phi x bar, and then you know that you have the right and left derivative. So let's say this is the slope of the right derivative. So let's say d plus phi in x bar. So this is different by x minus x bar, phi x bar plus. And I'm saying that this segment is less or equal than phi of x. It's because of this inequality, no? So if you take, assume, so from this inequality you have that phi, okay, this is not written, but on the other hand, so if you take a point, we know that the slope is decreasing. the incremental ratio is decreasing. Is decreasing here. This tells that this guy is larger than that guy, in particular, this guy is larger than this guy. It's the same, no? When you say that is monotone increasing, I'm saying that his incremental ratio is decreasing when I approach from the left, from the right. So when I take the limit, all these points are above the limit. And when I do the same on the other side, well, on the other side, I know that this one is less than this one. So here is above all this, the straight line with these slopes, in particular when I take the limit, is above to the limit. Vice versa, I can do also from the left. And from the left, I obtain another curve, another slopes. So I have also phi x bar, the derivative from the left. And now I can take convex combination. Because if you make a convex combination of the two, this is invariant, this is invariant, this is invariant, what changes is just this guy. So for all p, the same holds. X minus x bar, phi of x. And this is another possible definition of convex function. For all points in its graph, there exists a supporting line. Okay, so but your classmates said that we can prove with simple functions, and then it's a nice exercise. So let's do that. This is a very nice exercise. Okay, how to prove for simple functions. So first statement, is it true that I have this, if it holds for simple functions, then it holds for any function? Why?
Yes, phi continuous.
Hmm?
Phi continuous.
Phi is continuous, and why they do the integral converge?
The limit,
Because they, well, simple function converge uniformly.
yeah.
Okay, yes, it is enough. For f is the sum, let's put also the joint. Okay. So it's phi of the sum. So Ci, the measure of Ei, sum Ci, phi of, sum phi of Ci, the measure of Ei. Is that, no?
Yeah.
When I just assume a simple function, just integrate.
Yeah, because
Now.
from the definition of the convex function there by lambda,
Okay?
by recurrence we can prove that if we have n positive numbers for which the sum is equal to 1, then phi of the sum of lambda I xi is less or equal to the sum of lambda I phi of
Yeah.
xi.
If the p graph is convex and I give you n points here or inside, doesn't matter, I take and if sum lambda I is equal to 1, lambda I greater or equal than 0, and let's say x, y are in the x, y, y are in the epigraph of phi, then the sum xi, yi is in the epigraph.
Yeah.
Now,
Convert.
Now we can suppose that the measure of the E is 1, the measure of the interval. Yeah,
it's already 1.
yeah,
So this is equal to the lambda I.
yeah, so then it's possible.
And then it's a statement.
Yeah.
Okay? So which proof you prefer? I don't know. The other is the classical one. Okay, so now I start with the Bert here, and I would like to finish. Is that okay for you? Maybe you want to have an exercise now instead of doing the Bert theorem. What do you prefer, starting Bert theorem or one exercise? Exercise. Okay, I just. See what I selected here. So, let alpha I greater or equal than 0, sum over alpha I is equal to 1. And actually, whenever you see sum equal to 1, it means that it's a convex combination. Then, for all psi I greater or equal than 0, or greater than 0, the product psi I to the alpha I is less or equal than sum to the power alpha I psi I. Okay. There exists a convex function behind, which is there is only one.
We can take
Dx. Yeah, is the exponential. Okay. So this product is e to the
E ln sum.
okay. Now E is convex.
Why?
Hmm?
Why E is convex?
The exponential.
Yes, we haven't.
The n over the xn is equal to the rho x greater or equal than 0. Greater than 0 actually. So the second derivative is greater than 0. The first derivative is increasing. If I see 2 is okay. It's strictly convex actually. Okay, so let's apply Jensen.
This is just a little sum of CI logarithm.
The sum that's it.
But the logarithm of CI is less or equal to
What is equal to? I take positive exactly to avoid that. If it is 0, well, there is nothing to be proved. Okay. Okay, let's go back because I'm pretty advanced. I think it's in. Let's slow down a little bit.